In the last episode, we discussed the classification of chemical reactions. When you look at what happened between the reactants, a chemical reaction can be classified into one of the 5 categories: combination, decomposition, displacement, exchange, and combustion. Another way to look at a chemical reaction is to look at if there is a transfer of electrons between the reactants during the reaction. In that way, all chemical reactions can be classified into one of the 2 categories: redox and non-redox. In this episode and the next one, we're going to focus on the redox reaction. But the first question we have is, how are we supposed to know whether there is a transfer of electrons in the reaction? In other words, how do we predict if a reaction is a redox or not? To do that, we have to introduce a new concept that is called oxidation number. Oxidation number is a concept that we can use to predict if there is a transfer of electrons during the reaction. But what is it? How can we use it? Well, oxidation number, which is also called oxidation state. Oxidation number basically indicates if an atom is gaining or losing electrons when it is bonded with other atoms. Basically, it describes the electron situation around an atom. That's called oxidation number and oxidation state. So, how do I know the number then? There are 2 different situations. First one, if an atom is an ion, then the charge of the ion is considered the oxidation number of the atom, which makes sense. Okay, it is the charge of atom basically indicates whether that atom is losing or gaining electrons when it bonds with the other atoms. So it describes the situation of electrons around it. So the charge of the ion is the oxidation number for a monatomic ion. For example, sodium ion charge is 1 plus. We will say oxidation number is +1. Oxide ion 2 negative, -2. So basically the charge is the oxidation number. The only difference is that when we say oxidation number, we put the sign, the positive, negative, ahead of the number. What if an atom is covalently bonded with another atom? Well, here we go. It is the charge that the atom appears to have when the electrons in each bond is assigned to the more electronegative of the 2 atoms involved. What is talking about? Well, let's go through this by looking at a few covalently bonded together atoms. Let's look at the molecule hydrogen chloride. This is the covalent compounds because both elements are nonmetals. All right, so the statement tells you that in order to figure out the oxidation number for these kind of atoms that are covalently bounded together, you will assign the electrons in the bond will be assigned to the more electronegative of the 2 atoms involved. Okay, we'll assign these shared electrons to chlorine. Chlorine is more electronegative than hydrogen. When that happens, if this one totally goes to chlorine, hydrogen's lost it. If that is the case, hydrogen will carry a plus charge, chlorine is going to carry a negative charge. Does that make sense to you? So if that is the case, hydrogen will appear to carry a 1 plus charge, chlorine will appear to carry 1 negative charge. As a result, we will say chlorine's oxidation number is -1, hydrogen oxidation number, in this case, +1. Let's look at a different scenario. Carbon dioxide. Well, carbon dioxide, the Lewis structure of carbon dioxide. Now, in this case, oxygen is more electron negative than carbon. So let's assign all the shared electrons to oxygen. This 4 goes to oxygen, this 4 goes to oxygen. When that happens, it appears that oxygen is carrying a 2 negative charge, And it appears that carbon is losing 4 electrons, 2 over here lost to 1 oxygen, 2 here lost to another oxygen. So carbon appears to carry a +4 or 4 plus charge. So the oxidation number for carbon in carbon dioxide is +4. For oxygen in carbon dioxide is -2. That is what it's talking about. Well, for smaller, simpler molecules, we can do this. We can do this according to what is described here. Okay, just assign the shared electrons to the more electron negative atom, and let's see what kind of charge each atom will carry when you do that. Well, for more complicated formulas or compounds, molecules, it is not that easy to do this. Luckily, now let's go through some shortcuts for assigning oxidation numbers. But before that, let me remind all of us again about the purpose of learning oxidation numbers. Our goal is that to use the oxidation numbers to predict whether a reaction is a redox or not, to predict if electrons are transferred during a reaction or not. So let's go through the rules for assigning oxidation numbers. Number 1, oxidation number of an element in its elemental state is 0. When an element is staying by itself, when it is not combining with any other element, when it is not in a compound, the oxidation number is 0. For example, copper, silver, hydrogen, oxygen. These are elements in their elemental states. Oxidation numbers for them 0, 0, 0, 0. Which makes sense. They are staying by themselves. They are not losing or gaining electrons to any other element. So their oxidation numbers are zeros. Oxidation number for a monatomic ion is the same as the charge on the ion. We covered this on the last slide. For a monatomic ion, the charge is the same as its oxidation number. Number 3, group 1A plus 1, group 2A plus 2. This is a little confusing. The complete statement for this one should be, when in a compound, a group 1A metal will have a +1 oxidation number, a group 2A metal will have a +2 oxidation number. Okay, it must be when they're in the compound, because for example, sodium, that's a group 1A metal. If sodium is by itself, the oxidation number is 0. Only when it is in a compound, sodium chloride, now this sodium has a +1 oxidation number. All right, so this is number 3. Rule number 3 is actually a part of rule number 2. We all know that when in their compounds, group 1A metals will have a +1 charge. Group 2A metals will have a +2 charge. We know that, so it is basically a part of rule number 2. Hydrogen +1 in covalent compound. That comes handy. It's easy. So hydrogen, H2O, that's a covalent compound. They're both nonmetals. You don't need to think about it. Hydrogen will be plus 1. Okay. Ammonia, NH3, covalent compound. Hydrogen will be plus 1. So that comes handy. That helps. Oxygen -2 in covalent compound, except in peroxides. Well, oxygen CO2, we just did it in the last slide. CO2 carbon dioxide is a covalent compound. Oxygen is -2. Water, oxygen -2. Okay. Well, peroxide, hydrogen peroxide. This is one of the most common peroxide we're going to encounter. In this case, in peroxide, 2 oxygens bonded together with other elements after that. Then oxygen is -1. Hydrogen plus 1 hydrogen. This is hydrogen. This is oxygen. In binary molecular compound, the more electronegative element is assigned a negative number equals to its charge in binary ionic compounds. All right, let's again use an example to go through this. A binary covalent compound, HCl, a binary molecular compound, HCl. Both are nonmetals, so it's a molecular compound. The more electronegative element, chlorine, the more electronegative element is going to be assigned to a negative number equals to its charge in binary ionic compounds. What kind of charge chlorine is going to carry when it is in the ionic compounds? Do you remember how to do that? Octet rule. Chlorine is in column number 7A. To satisfy octet rule, it needs one more electron, which means chlorine will form a 1 negative charge in ionic compounds. If that is the case, then chlorine will have a -1 oxidation number. That's what this statement is talking about. In binary molecular compounds, the more electronegative element will be assigned a negative number equals to its charge in binary ionic compound. For a compound, the sum of oxidation numbers equals 0. For a polyatomic ion, the sum of oxidation states equals the charge of the ion. What this is talking about. So CO2, that is a compound. We know that oxygen is going to be -2 oxidation number. How do we know that? It's right here. Number 5 told us. If oxygen is -2, carbon has to be +4. Carbon has to be +4. Why is that? Because the oxidation numbers for all the atoms in the formula so sum together to 0. So oxygen is -2. We have 2 oxygens. 2 oxygen will be -4 together. Therefore, carbon has to be +4 in order for them to add to 0. So far, so good. -2 +4 equals 0. So carbon is +4. For a polyatomic ion, sum of the oxidation numbers will equals to the charge of the ion. So let's do this. SO4 to negative sulfate polyatomic ion. Let's figure out the oxidation numbers for oxygen and for sulfur. For oxygen, easy, -2. How do you know that? Item number 5 told us that right away. So oxygen will be -2. Sulfur, what we don't know. Let's see. We have 4 oxygen, 4 times -2. 4 oxygen will contribute -8 to the whole formula. -8 plus whatever is from sulfur, they should equal, you add them together, they should equal the charge of the ion, which is -2. The charge of the ion. So -8 plus the oxidation number of sulfur should equal -2. As a result, the sulfur oxidation number has to be +6. -8 plus 6 equals -2. The sum of the oxidation numbers for a polyatomic ion will equals the charge of the ion. All right, let's do some exercise together. Find the oxidation numbers for each of the elements in the following compounds or formula, I'll say. Let's do the bottom one together. Sulfur fluoride. This is a binary covalent compound because they are both nonmetals. Binary covalent compound, the more electronegative element will be assigned a negative number equals to its charge in an ionic compound. Fluorine again is in column number 7A. In the ionic compound, fluorine will carry a 1 negative charge. Therefore, its oxidation number is -1. Are you guys following me? This is rule number 6 on the last slide. If fluorine is -1, rule number 7 tells us the oxidation numbers for everything else together should equal 0 because it is a compound. If fluorine is -1, you have 4 fluorine atoms, so you have -4 altogether, so the sulfur has to be +4. Make sense to you? If you understand this, do phosphate chloride. You can pause the video, do this one. Okay, this is basically also binary molecular compound, which follows rule number 6 on the last slide. Once you're done, come back, we'll do the others, and after we finish, we'll look at the answer key. All right, now let's look at manganese oxide. Oh, this is an ionic compound because it is a metal, nonmetal. Ionic compounds, oxygen, -2. If oxygen is -2, there are 2 oxygens, so that's a -4. Manganese, in this case, will be +4. Are you guys following me? Carbonate ion follows the number 7. All the oxygen numbers as together will be 2 negative or -2. All right, again, in this case, we work on oxygen first. Why? Because we know oxygen is -2. So oxygen will be -2. How do you know that? Rule number 5 tells us oxygen is always -2 unless it is in the peroxide. If oxygen is -2, 3 oxygens will give us -6 altogether. What will be the carbon then? Whatever carbon is plus -6 will equal -2, which is the charge of the ion. As a result, carbon will be +4. So carbon +4, oxygen -2. The last one, potassium dichromate. This is a little challenging. Okay, there are 3 elements. Which one do we work on first? Of course, we work on the ones that we know them right away. Oxygen, we know -2. Potassium is an element in column number 1A, so we know it is +1. Now we need to add them up so that they will add up to 0. In this formula, we have 2 potassium, that's 2 times +1. So potassium contributes 2 times +1 to the formula, plus 2 chromium. We don't know what the chromium oxidation number is yet, but we do know it's going to be 2 times whatever the oxidation number is for chromium. Then add the oxidation numbers from oxygen, which is 7 times -2. All of this adds up together should equal 0 because it is a compound. So 2 times +1, that's +2. So that's 2 plus 2 times whatever it is, that's our goal. We're going to solve that. -14, 2 times -2 times 7 equals -14 equals 0. So 2 times whatever the oxidation number for chromium is going to -12 is 0. -14 plus 2, that's -12 now. Now I assume all of us know this oxidation number needs to be 6. 2 times 6, which is 12. 12 minus 12 equals 0. So the chromium oxidation number in this case is +6. Potassium +1, chromium +6, oxygen -2. Are you guys following me? Here is the answer key for all of this. All right, we'll move on to the next slide. Well, here comes our goal of learning oxidation numbers. We use it to decide whether a reaction is a redox. To determine whether a reaction is a redox or non-redox, look for changes in the oxidation numbers of elements in the reaction. If there is a change in oxidation number before and after the reaction for any element, then that reaction is a redox reaction. If there isn't a change, that's a non-redox. Can we show an example? Yeah, let's look at an example. Let's look at the reaction between calcium and chlorine. The reaction is pretty violent. They involve a lot of light and heat. Basically, it's burning. Here is the reaction. Let's figure out the oxidation numbers for each element before and after the reaction. What is the oxidation number for calcium? 0, because it is in its elemental state. What about chlorine before the reaction? 0, because it is in its elemental state. Now, calcium is column number 2 metal, so it's 2 plus 2. Chlorine is element number 7A, it is -1. Now, when you look at this, the oxidation number for calcium changed before and after reaction. The oxidation number for chlorine changed before and after reaction. Therefore, this is a redox reaction. Are you guys following me? Practice, identify if each of the following reactions is a redox or not. All right, figure out all the oxidation numbers before and after reaction, then make a prediction. Well, basically, this is a single replacement reaction. Zinc replaced hydrogen out, if you can see. So zinc kicked hydrogen out. It is a single replacement or displacement reaction. So let's figure out the oxidation numbers. Zinc before the reaction 0 because it is in its elemental state. Hydrogen after the reaction 0 because it is in its elemental state. Sulfate, we don't need to worry about that because you can see before the reaction, after the reaction, it's sulfate. It didn't change. We know nothing changed for sulfate. You don't need to worry about the sulfur and oxygen in this case. You can do that. You don't have to. Hydrogen in the covalent compound, it is +1. We know that. Okay, it's in the shortcuts, in the rules for assigning oxidation numbers. Hydrogen +1. Zinc after the reaction, sulfate is 2 negative. Therefore, zinc is 2 plus. So oxidation number is plus 2. Sulfate is 2 negative. It carries 2 negative charges. How do you know that? You memorize it. All right, so zinc is plus 2. Now you can see zinc changed, oxidation number changed before and after reaction. Hydrogen, oxidation number changed before and after reaction. So this is a redox reaction. As a matter of fact, displacement reaction or single replacement reaction are always redox reactions. Sodium chloride plus silver nitrate produces silver chloride and sodium nitrate. Well, this is an exchange reaction or double replacement reaction. Before sodium is combining with chlorine, after the reaction, it is combining with nitrate. Before nitrate was combining with silver, afterwards silver combined with chloride. All right, so double replacement. If we remember what we did for the sulfate in the last example, you know nitrate, don't have to worry about it. It didn't change. It stays at nitrate. We know chloride in an ionic compound is -1. After reaction, still combined with a metal, -1. Chlorine didn't change. Sodium, we know it's +1 because it's column 1A metal. Sodium still +1. Silver +1, silver +1. None of them changed. This is a non-redox reaction. Again, as a matter of fact, a double replacement reaction or an exchange reaction is not a redox reaction. Exchange reactions are not redox reactions. Methane reacts with oxygen to produce carbon dioxide and water. Oh, combustion reaction, burning methane in oxygen. All right, oxygen is 0 before the reaction because it is in its elemental state. Oxygen after the reaction, -2 in the compound. Oxygen is always -2 in the compound. Oxygen is always -2. So oxidation number of oxygen changed. We don't even need to look at any other changes. If there is a change of oxidation number for any element, it is a redox. So this is a redox reaction. As a matter of fact, combustion reactions are always redox reactions. The last example, hydrogen reacts with oxygen to produce water. Okay, this is a combination reaction. Two substances combine together to form one product. If we do the oxidation numbers, this is 0, this is 0, this is +1, this is -2. This is a redox reaction. However, not all combination or not all decomposition reactions are redox or are non-redox. In the case of combination and decomposition reactions, you must use the oxidation numbers to predict whether reactions are redox. The three categories here, you'll know them right away. For combination and decomposition, you have to use the oxidation numbers. Well, this episode is a little long, but let me summarize quickly what we can do now. Given a reaction, we can predict if it is a redox or not. How to do that? Look at the oxidation numbers for each element before and after the reaction. If there is a change, that's a redox reaction. If there isn't a change, that's a non-redox reaction. All right, see you next time.